This is my second lecture on graphical sensitivity analysis. Previously, we discussed the a problem of a pottery company which was aiming to maximize the profit with some available resources. And we found out through our graphical method that point B is optimal, having x1 equal 24 and x2 equal to 8 and a profit of $1,360. So after finding the optimal solution through the graphical method, the next step is the sensitivity analysis. But first of all, we should understand that what is the purpose of sensitivity analysis. We look for answer of the following two questions in the sensitivity analysis. Our first question is that what if the coefficients of the objective function change? Then what is their effect on our optimal solution? The second question is if the right hand side of the constraint changes, how is it going to affect our optimal solution? But why these coefficients and right hand sides of constraint change? It's another question. That's because the coefficients are at best estimates. The prices, the cost, the profits, they can change. And similarly, the resources available, they are also likely to change. So the management would want to know that the optimal production plan they have derived earlier. In our case, we found that the optimal point is B. So the management wants to know that if the earlier developed plan, is it still viable in these changing conditions? So let's find out this thing. In this video, in order to keep it short, I'll focus on the first question, and that is how the changes in the coefficients of objective functions affect the optimal solution. So before starting the analysis, we should look into the following three important concepts that will be repeatedly used in the sensitivity analysis. The first concept is about slopes. We all know that the equation of a straight line is given as y is equal to mx plus b, where b is the y-intercept and m is the slope of the line. So let's say if we have a general equation of line as ax plus by plus c equal to 0, where a is the coefficient of a is the coefficient of x, b is coefficient of y, and c is constant, then we can derive its slope as m is equal to minus coefficient of x divided by coefficient of y, and we can denote it as minus cx over cy, and the coefficient of x is a and the coefficient of y is b, so it will be simply minus a by b, provided b is not equal to 0, because if b becomes 0, then the slope becomes undefined. So let's apply this on our objective function. This is our objective function. We can rearrange our objective function as 50x2 equal to z minus 40x1, or x2 is equal to z by 50 minus 40 by 50x1. Now this equation x2 is analogous to the general equation of a line, because in our case we have defined x1 on x-axis and x2 on y-axis. So the y-axis corresponds to x2 in our case, and x1 corresponds to the x. So this 40 by 50 is basically the slope of the equation. So whenever we come across an equation, we can derive its slope by simply writing m is equal to minus cx by cy, or minus coefficient of x over coefficient of y. Because we don't have x and y, we have replaced it with x1 and x2. We will simply write minus c1 by c2, and it will be equal to minus 40 by 50. In a similar fashion, we can also find the slopes of our constraints. So we know this, that the slope of the objective function is minus c1 by c2, and that is equal to minus 40 by 50. Similarly, for the labor constraint, we can write it x1 plus 2x2 equal to 40 equal to x2 is equal to 40 by 2 minus 1 by 2 x1, where 1 by 2 is the minus 1 by 2 is the slope of the line. Or we can simply use the formula that we just discussed, that slope is equal to minus c1 over c2, or coefficient of x by coefficient of y. It is equal to, in this case it will be, the coefficient of x1 is minus 1 and coefficient of coefficient of x1 is 1 and coefficient of x2 is 2. The slope is minus 1 by 2. So applying the same formula here, the slope will be minus 4 by 3. So these slopes will come handy when we are going to discuss the sensitivity analysis. The second concept is what happens when we change the coefficient of x1. In order to understand this thing, let's see a simple simple graph of an equation. So when the coefficient of x1 or x2 changes, the slope of the line changes. So the graph shown here is for a line for 40x1 plus 50x2 equal to 1200. So now to demonstrate our point that whenever we change the coefficient of x1 or x2, here we are focusing on x1. So whenever we change the coefficient of x1, it will change the slope of our line. So let's say we change the coefficient of x1 and keep the other variables and constants same. So we have 100x1 plus 50x2 equal to 1200. So this equation can be plotted by putting x1 is equal to 0 and x2 will be 24, and when x2 is equal to 0, x1 will be 12. So using these 2 points, that 0, 24 and 12, 0, we can plot it. So it's plotted here. So as you can see, the red line for the increased x1 coefficient, it has become more steeper. The slope has changed. Now let's see when we decrease the coefficient of x1, then I have placed another equation here, that is 30x1 plus 50x2. Only the coefficient of x1 has been reduced from 40 to 30, and the remaining variable and the constant have been kept constant. So this equation can also be plotted by on 2 points, when x1 is equal to 0, x2 is equal to 24, and when x2 equal to 0, x1 equal to 40. So when I'll plot this line, and it's shown here in the green color, you can see that this line has become flatter as compared to our original line. So in a nutshell, we can see that when the coefficient of x1 increases, the line becomes steeper, and when the coefficient of x1 decreases, the line becomes flatter. Now let's see what happens when we change the coefficients of x2. Again, we say that the slope of the line changes, and we have shown here a graph of a line of 40x1 plus 50x2 equal to 1200. So let's demonstrate that what happens when the coefficient of x2 increases. So I have kept the 40x1 at its original value and have changed the coefficient of x2 to 100, and the constant is again 1200. Now this line can be plotted using the same methodology discussed before, that is when x1 is equal to 0, x2 equal to 12, and then when x2 is equal to 0, x1 is equal to 30. Now this red line, it shows the situation when the coefficient of x2 is increased, and as you can compare, if you compare this red line with the original blue line, then you would see that this line has become flatter. And now we want to see that what happens when the coefficient of x2 decreases. So let's again plot an equation of a line where the coefficient of x1 and the constant are constant. Constants are kept at their original value, whereas the coefficient of x2 has been reduced to 30 from 50. So it can be plotted at point 0, 40 and 0, 30, 0. So you can see the line has become steeper. So Based on this discussion, we can say for x2, whenever the coefficient of x2 increases, the line becomes flatter. Whenever the coefficient of x2 decreases, the line becomes steeper. So after slope and the effect of the coefficients on the slope, let's discuss another important concept that is known as the multiple solutions. So whenever the slope of an objective function it becomes equal to the slope of a constraint, we have multiple solutions. So in order to demonstrate this, let's say that initially the slope of our objective function it becomes slope of the clay constraint. So here this problem in this figure, this is the original problem that we derived in our last video, and it was also shown on the very first slide. This is our objective function 40x1 plus 50x2. This is our clay constraint and this is our labor constraint. Now if somehow I change the slope of this objective function and I rotate this line, I rotate this line towards the clay constraint so that its slopes becomes first parallel to the clay constraint. You can see now clay constraint and this objective function line, they have become parallel, and if I push it further towards the optimum point, then it will be overlapping the our clay constraint. So initially we just had B as our optimal point, but now you can see that point C has also become an optimal point. So that means whenever the slope of the objective function becomes equal to a constraint, we have multiple solutions. Now let's see what happens when we change the slope of objective function equal to the slope of the labor constraint. So this is again our original problem where the objective function had this slope, this equation, and a slope of minus 40 by 50. I try to rotate it towards the labor constraint. So when I rotate it, first it becomes parallel to the labor constraint, and then if I push it away from the origin, since it's a maximization problem, and I push it away so that it can reach the boundary of the feasible region, so this objective function it becomes overlapping and it overlaps the labor constraint. So initially we just had this B as the optimal point, but now if you look at here, the point A will also become optimal. So whenever the slope of the objective function it becomes equal to the slope of the constraint, we have multiple solutions. Now after understanding these three concepts of the slope, the effect of coefficients on slope, and multiple solutions, now we dig deeper into the sensitivity analysis. So this is our original problem where this is objective function, was our labor constraint, and this is our clay constraint. Straight away we can write that the slope of the objective function is minus 40 by 50, and this is minus 1 by 2, and this is minus 4 by 3. So the sensitivity range of an objective function is a range of values over which the current optimal solution point will remain optimal. So our current optimal solution was point B. So what we are saying here is that the point B should remain optimal, and we want to find the range over which this point B remains optimal. We'll come to this point in a bit. So but for the purpose of doing this sensitivity analysis, let's define C1. We have already described what is C1, that coefficient of x1. Now we are defining C1 as a sensitivity range, that is the range of the values that the coefficient of x1 can take. And we define similar in a similar fashion, we define C2, which shows the range of the values the coefficient of x2 can take. So what really we want to know in this analysis is that how much change can we make in the coefficient of x1 and still our original optimal point B still remains optimal. But remember this is very important thing, that in doing so we might have multiple optimal solutions, but point B will be one of the optimal solutions. This is the basic requirement of the sensitivity analysis, that our originally obtained optimal point should stay remain optimal. Okay, so now, as I discussed earlier, that the slope of the objective function is simply minus C1 by C2 or minus 40 by 50. So, in order to find the sensitivity of the coefficient of x1, we will write our slope as minus C1 by C2 is equal to minus 40 by 50. Remember, 40 is the coefficient of x1 and 50 is the coefficient of x2. Now, if we want to analyze the impact of C1, that is the change in the coefficient of x1, we will keep the x2 coefficient of x2 at its original place, and we will replace the coefficient of x1 with C1. So we will write minus C1 by 50. Similarly, for analyzing the impact of C2, we will keep the coefficient of x1 at its constant value, that is the previous value, that its original value, that is 40, and we will replace the coefficient of x2 with the term C2. Now, this shows us one of the limitation of this sensitivity analysis, that we can only make one change at a time. We cannot change the coefficient of x1 and x2 together. So first we find the range of coefficient of x1, then we find the range of coefficient of x2. So in our first step, we find the range of coefficient of x1, and we discussed earlier in the previous slide, if I go back, that when we want to find the range of x1, we keep the coefficient of x2 at its original place, and we just write minus C1 by 50. And how are we going to do it? I'll show you in a bit. So we want to find the maximum value the coefficient of x1 can take, and the optimal solution B, it still remains optimal. So, and we have discussed earlier in the earlier slides that whenever we increase the coefficient of x1, the line would become steeper, and that means the slope would change. So objective function will become steeper, but the question is how much steep the objective function can become when we increase the value of x1. So we know that our feasible region is defined with the help of two constraints, the labor and the clay. So we look at these two constraints and we see that the clay constraint having a slope of minus 4 by 3, it is steeper as compared to the labor constraint having a slope of minus 1 by 2. So this is labor and this is clay. So when answering to the question that how much steep the objective function can get, we say that the slope of the objective function can become equal to the slope of the steepest constraint. Now we have to understand that while choosing the steepest constraint in the problem, we have to make sure that this steepest constraint should be passing through the optimal point B. Well, in this case we have just two constraints and both are passing through point B. Well, in the next few videos I'll discuss that when we have more than two constraints, three constraints, then there might be a possibility that at the optimal point one of the constraint is not passing through it. So when we are choosing the steepest constraint to equate the slope of the objective function to it, we should choose the constraint that is passing through our optimal point. And in this case, the steeper constraint is clay, and that clay constraint is passing through B. So we will write it as minus C1 by 50. It is equal to, because we can make the slope equal to the slope of the steepest constraint, and that is the clay constraint. So we will write it equal to the slope of the steepest constraint, clay constraint, and the slope of the clay constraint is minus 4 by 3, and the slope of the labor constraint is minus 1 by 2. So we will put it equal to minus 4 by 3. So C1 is equal to 200 divided by 3, or equal to 66.67. So that means that coefficient of x1 can have the maximum value of 66.67, and we will still have point B as one of the optimal points. So let's check this thing. Now in the graph, as you can see here in this graph, I have overlapped the objective function with the clay constraint, and this is showing us that they both have the same slopes, and they both have the same slope. Now let's check that the maximum value that we found, 66.67, it it is can it still give us the point B as an optimal point? So what we do is we rewrite our objective function, and in our objective function we replace 40 with 66.67. That is the maximum value that we just found, and we keep the remaining coefficient of x2 and the constraint. We just keep them the same. Now we check all the 3 points, the profit given by this equation at all the 3 points A, B, and C. So at B point, that was our optimal point, had the coordinates of 24, 8, the profit is $2,000. At C point, which has a coordinate of 30, 0, and when we plugged in these coordinates into our changed objective function, we still got the $2,000. And at point A, the profit is $1,000. Now we can see that in addition to point B, point C has also become an optimal point. So from here we can conclude that the maximum value, if the value of 66.67 is placed in as a coefficient of x1, we will still end up with point B as an optimal. Now let's do another test. Let's say if we exceed the value of coefficient of x1 from 66.67 to a higher value, let's say 70. So now we rewrite our objective function again. This time we have placed 70 as the coefficient of x1, and the coefficient of x2 has been kept at its original position, and similarly the constraints have also been kept at their original state. Now let's find the profit at point A, B, and C. So at the profit at B, using the coordinates 24, at it's $2,080. At point C, with the coordinates of 30, 0, the profit is now $2,100, and point A, the profit is $1,000. Now you see that initially we had point B as optimal point, but right now we have point C as the optimal point. So this is violating our requirement, as B is no longer optimal, instead C is optimal. So now let's see what is the minimum value of the coefficient of x1, and when we decrease the coefficient of x1, we know the slope changes, and more precisely we know the objective function line, it will become flatter. We discussed in the start of the lecture, but the question is how much flat it can go. And again, similar to the previous discussion, our Our feasible region is defined by, here in this question, defined by two constraints. One is steeper, one is flatter. So the objective function can become flatter uh, by putting its slope equal to the slope of the flattest constraint, and in our case the flattest constraint is clay. But again, this is a very important check, that when we are choosing constraints, and we must make sure that this constraint must be passing through the optimal point, in our case the point B. So now the flatter constraint is labor. So now we will do analysis that we in this an analysis similar to the one that we did in our previous slide. Minus c1, that is the range of the coefficient of x1. 50 is the coefficient of x2. We are not changing it, so we have kept it constant. Now we will put the slope equal to slope of the flatter constraint, that is 1 minus 1 by 2. I'm writing here again the slopes of the objective function, that is minus 40 by 50. This is minus 1 by 2, and this is minus 4 by 3. So here c1 is equal to 50 divided by 2, minus they can cancel, so c1 is equal to 25. So we found that the minimum value of the x1 coefficient is 25, and if we put 25 instead of the 40, we will still end up with point B as an optimal point. So let's check it, and let's replace the coefficient of x1 40 with the 25, and keep the x2 coefficient at its original value. Now let's find out the profit, and before finding the profit, just have a look at this figure. In this figure you can see that I have overlapped the objective function with the labor constraint, and initially we had this point B is optimal, and based on our discussion on multiple optimal solutions, we can say that point A should also be optimal. So let's check it out. So profit at point B at the coordinates 24 8 is $1,000. At C it is with the coordinates 30 0, it's $750, and at A 0 comma 20 it's $1,000. So we see that $1,000 at both at the point B and C. So we can see that the point B is optimal along with point A. So again, point B still remains optimal. Now let's see what happens when the coefficient of x1 goes below 25. Let's say 20. We again change the value of our objective function, and we write it as z is equal to 20 x1 plus 50 x2. We again find the profit z at 3 points A, B, and C. So I have not written it in the order A, B, C. I have just written it like in the order of B, C, A. So it doesn't make a difference. So at B it is $880, and at A it is $1,000. Now the optimal point is not B, rather it has become A. Now this is against our requirement. This is violating our requirement, and B is no longer an optimal point, which was our requirement at the first place, that the original optimal point should remain optimal. Instead, the point A has become optimal. Based on this discussion, we can say that the range of the coefficient of x1 is from 25 to 66.67. We have checked it, we have tested it, and we see that any value exceeding 66.7, or any value falling below 25, it will change the optimal point B to another point C or A, whatever it is. Now let's see let's see what happens when we change the coefficients of x2. We will go through a similar procedure, so I'll be a little quick this time to shorten the video. So we have this original profit, this labor, this constraint. We know the slope of the objective function is minus 40 by 50, and this is minus 1 by 2, and this is minus 4 by 3. So in a similar fashion, we see how what is the range of coefficient of x2. First, we need to find the maximum value that the coefficient of x2 can take. We know that when we increase the coefficient of x2, it changes the slope, and we discussed in our previous in the initial part of the lecture that objective that the line when it becomes flatter when the x2 increases. So but how much flat it can go, again the question, the same question that we discussed in our previous slides. So the slope of the objective function line, it can become equal to the slope of the flattest constraint, because our feasible region is defined by the constraints. So we will look for the flattest constraint, but we have to make sure that this flattest constraint must pass through point B. In our case, it's a labor constraint, and it is luckily passing through the point B. So with this discussion in mind, now we will find out the value of the maximum value of the coefficient of x2. So now, as we are not looking into the change of the coefficient of x1, we will keep the x1 coefficient at its original value, and we will replace 50 by c2, and this should be equal to minus 1 by 2, which is the slope of the flattest constraint. So that means it is equal to minus minus gets cancelled, and c2 is equal to 80. So what we find here, that the coefficient of x2 can at max take a value of 80, and point B will still remain an optimal point, and another point would add into it, would become optimal along with B. So let's again check it. So maximum value of 80. Now if I replace this 50x2, the coefficient, original coefficient 50, with the 80, and I find the profit at points A, B, and C. So I see that now before doing so, just also have a look at the figure where the objective function is now parallel and overlapping the labor constraint. So we find the profit at point B, C, and A, and we see that the profit in B and A are $1,600, and these both points are optimal. Now let's see what happens when we exceed from 80. Let's make it 90. Then our objective function will become 40x1 plus 90x2. Now again finding the profit at these 3 points, and we will see here that instead of B is no longer an optimal point. B instead, A has become an optimal point where the profit is $1,800. Now B is no longer an optimal, and this is violating our requirement. So we can say that the maximum value the coefficient of x2 can take is $80. Now let's find out the minimum value in a similar fashion. I think I have done this thing like 3 times before, so you should be able to do it, but I'll just guide you through the steps. The minimum value of coefficient of x2, for that we have to decrease the coefficient of x2, and we know when we decrease the coefficient of x2, the slope changes, and precisely what happens, the line becomes steeper. The question again is how much steep it can go. We'll again look at the constraint, and we find that the slope of the objective function can become equal to the slope of the steepest constraint. But again, we should remember that this steepest constraint must pass through the optimal point, which in our case is B. And and in this problem, the steepest constraint is clay. So what we do, we again do the same procedure. We keep the coefficient of x1 at its original position right here, c2, and this is equal to what's the slope of the coefficient function. This is minus 4 by 3, this is minus 1 by 2. So if we put it equal to minus 4 by 3, so that means c2 is equal to 120 by 4, and that is 30. So initially we found the maximum value of 80, so the minimum value is 30. So you can check it by yourself, because I think the video has become quite long by I think you should try it yourself, that what happens when you reduce the value of the coefficient function, and you make it to a value less than 30, what happens? So in a nutshell, the range of the x2 coefficient is from 30 to 80. So I hope in this video you must have understood the basic concept behind the changing the coefficients of objective functions. I have tried to make it as simple as possible, and in this process the video's length has gone a bit longer. But anyways, in the next lecture I'll discuss with you that how the changing the right hand side of the constraints changes affects our optimal solution. Thank you.